Sticking with our 5 kilogram bowling ball, more realistically, when things are far from Earth, they're not going to be at rest. So 400 kilometers away in orbit basically means it's moving. For any object, the total energy it has as it's moving, flying around in the vicinity of Earth is going to be the kinetic energy plus the gravitational. Kinetic energy is always 1/2 mv squared, and it's always positive. Gravitational is always negative of gmm over r. So our total energy for anything is always going to be 1/2 mv squared minus gmm over r. We did a little bit of satellite work when we talked about centripetal motion. When an object is in orbit, it's going in a circle, so that turns into an F net equals ma situation. The only force acting on our object is the force of gravity. It's got a value of gmm over r squared since it's the force. That's what makes it go in its circle. Since it's going in a circle, the a becomes v squared over r. If we clean that up, we get that v squared equals gm over r. To find the total energy of our satellite, we need to know the speed. So this little stuff I did here in purple gives us a value of the speed. As we talked about in centripetal, there's a connection between how high something is and what its speed is. So we now know v squared, or at least an expression for v squared. I can substitute that in to our general equation for total energy. Oops, that's a little bit messy. That's a capital G in there. When I sum that in, my E total becomes 1/2 of m gm over r minus gmm over r. If I clean that up a little bit just to make it more obvious, I've got 1/2 gmm over r minus gmm over r. If I clean all that up, we've got kind of a common denominator thing going on, or however you want to do it. We've got 1/2 of a gmm over r, and from that we're subtracting a full gmm over r. That means we're going to get negative 1/2 gmm over r. Total energy is always the kinetic plus the gravitational, but for a satellite in a stable orbit, since we've got this expression for v squared, we get a specialized version of E total. For an object that's orbiting, the total energy is always negative 1/2 gmm over r. You can use that for any satellite question. Using that with our bowling ball, oops, let's do a little doodle over here. It was 400 kilometers above Earth, so that's 400,000 meters, and the radius of Earth is at 6.37 number. So the r that we're going to plug in is 6.77. So our E total is negative 1/2 the G value, 6.67 times 10 to the negative 11. The mass of Earth, 5.97. Oops, bad screen management. Let's move this out of the way. .97 times 10 to the 24, and then the mass of our bowling ball was 5. All of that divided by the R value. If you're 400 kilometers above Earth, the R value is 6.77 times 10 to the 6. Clean that up, crunch it out, and I get an E total. It's going to be a negative number as expected. Even though it's orbiting and seems to be far from Earth, it's still trapped. The bowling ball is not going to fly away into deep, deep space unless we give it energy. And the value is negative 1.5 times 10 to the 8 joules. If you look back, this is a big negative number, implying that the bowling ball is trapped. But if you look back at the question we did where the bowling ball was just at rest at 400 kilometers, being at rest at 400 kilometers, it's more trapped. It's standing still, so you've got to get it moving and get it far from Earth. So in that standing still situation, you got an even bigger negative number. When the bowling ball's out there already moving, it's trapped, but it's not as trapped. It's got a little bit of positive kinetic energy, or the fact that it's moving would make it a little bit easier to drag it out of the well of gravity if we wanted to do that.